Aboard the Submarine of Learning. My name is Alondra, my partner's name is Deborah, and today we are going to be talking about ocean acidification and coral reefs. So let's dive in. We are now entering coral reefs. Though coral reefs only take up 1% of our oceans, it is home to nearly 25% of our ocean species. Some of these species include sea turtles, sharks, fish, and of course, Nemo from Disney's Finding Nemo. Coral reefs are extremely important as they not only provide habitat but also protect our coastlines from storm and wave action and reduce coastal erosion. Coral reefs are made up by coral polyp structures, which are small organisms protected by a calcium carbonate skeletal structure. As carbon pollution increases, these structures are being harmed by ocean acidification. So, what exactly is ocean acidification?
Thank you, Alondra. Hi, everyone. This is Deborah, and I'm going to give you an overview of the process behind ocean acidification. What is it? How does it work? Ocean acidification describes the decrease in the ocean's pH. pH is used to tell us how acidic or basic a liquid is usually, so really strong acids and really strong bases are on opposite sides of this scale. Right now, the ocean is at about an 8.1, so it's a little bit more basic than the water that we drink. But the pH has been lowering in recent years, and this tells us that the ocean is getting more acidic, so that's where we get the term ocean acidification. Now, what causes it? The major contributor right now is carbon dioxide pollution. You've probably heard before that humans have really increased the amount of carbon dioxide in our atmosphere, and this can be from fossil fuel emissions like cars, airplanes, other vehicles, and even factories who use fossil fuels. You've also probably heard more often that carbon dioxide contributes to climate change or global warming because it is a greenhouse gas. And I just wanted to make a very clear distinction. Greenhouse gases, while they are known for contributing to climate change and ocean acidification are two completely separate processes, and the one thing that they have in common is carbon dioxide. Fossil fuels are just one example of how we contribute to carbon pollution, but there are other things causing this as well. So I really encourage you guys to go out there and do your research, find out where else carbon dioxide comes from, because unfortunately we don't have time to go over all of that right now, but there are a lot of different sources and a lot of different ways that humans contribute carbon, and that all leads up to ocean acidification. So with that being said, let's get into the science behind the process. So ocean acidification is pretty much a series of chemical reactions, and don't be intimidated by the chemistry. It's really a simple concept, and there's going to be a demonstration in just a minute to show you what it looks like in action. Basically, carbon dioxide from the air dissolves into seawater and then reacts with calcium carbonate to produce these other things called bicarbonates. I know carbonate sounds very similar to bicarbonate, but they are very different things. Animals with hard shells take carbonates out of the water and combine them with calcium to build hard structures. Ocean acidification causes problems because bicarbonates are useless to these animals pretty much. They just need the carbonates and the calcium, but extra CO2 lowers the amount of carbonate in the water when it forms those bicarbonates that I just mentioned. So without the pure carbonate, animals can't build their shells or their skeletons. They would have no body structure without it. So this graphic is from BioAcid, which is one of the largest research projects currently studying ocean acidification. This foundation is centered in Europe, and it's important to know that research is happening all across the world because ocean acidification is not a local issue. This is something that has impacts all across the globe. This is a map from NASA showing the future of carbon dioxide in our atmosphere, and as you can see, atmospheric carbon doesn't follow geographic boundaries. You can't contain it with a fence or a wall. Once carbon is in the air, even if it's produced in the United States, it can travel across the world and impact coral reefs in Australia or Mexico or any number of places. So here is a demonstration of what ocean acidification looks like in action. This is the rubber egg experiment, and this video comes from the Sci Guys on YouTube. And this is something you can totally do at home too. It's actually really fun. All you have to do is put an egg into a glass, add enough vinegar to completely cover it, and then let it sit for about a day. Almost immediately after putting the egg in the vinegar, you can see bubbles on the outside, and that's the carbon dioxide gas leaving. Vinegar is acidic, and as you can see, it dissolves the eggshell, but leaves the inside completely intact. And this is because the shell is made of, what's it made of? You guessed it, calcium carbonate. This is the exact thing that ocean animals use to make their shells. The calcium carbonate in the shell reacts with the vinegar to form carbon dioxide, and the rest of the shell is left as a liquid in the vinegar. The calcium doesn't just disappear, it's still there in the glass, but the bubbles show you that the carbonate itself is dissolving and leaving the calcium behind. Once all that carbonate is gone, the shell can't hold itself together anymore, and you're left with just the inside of the egg. So the rubber egg experiment is obviously a much faster process than what's currently happening with ocean acidification. So let's go back to the pH scale for a second. Like I said before, the oceans currently have a pH of about 8.1, so that's over here, and then the vinegar is about 2.3 all the way down here. So vinegar is much more acidic than seawater. But if you look right up here, this egg has about the same pH as seawater currently, and that tells us that if the ocean gets any more acidic than where it's at right now, shells will start to dissolve, just like the egg. This is a graph of the ocean's pH starting all the way back in the 1700s, and it also predicts future changes. So as you can see, the pH has been declining very quickly, especially since the last 50 years. So we can see already that it's been changing, and we can predict how it's going to change in the future. So now Alondra is going to tell you guys a little bit more about which animals and habitats are especially at risk.
Thanks, Deborah. So, as I mentioned before, corals are made up by polyps with calcium carbonate skeletons. Therefore, the availability of carbonate is essential for their survival. Researchers have found that ocean acidification impairs the growth and reproduction of coral reefs. Corals grow in two distinct processes: elongation, which is also known as upward growth, and densification, which is the lateral thickening of coral. Though both processes can be impacted by ocean acidification, researchers believe that densification is the process taking the hardest hit. To test this theory, a group of researchers exposed porite coral to low pH levels and measures the effect it had on both elongation and densification. And what they found was that densification was directly impacted by low pH levels, and in turn had the most damage. With this said, it's predicted that the skeletal density of porite corals can decline by 20.3% over the course of the 21st century. The major threat studied is reproduction, or more specifically, coral recruitment. Coral recruitment is responsible for successful fertilization, larval settlement, and survivorship. However, ocean acidification seems to be hurting recruitment, and in turn, hurting all of its responsibilities. In fact, when researchers exposed two groups of elkhorn coral to normal CO2 levels and high CO2 levels, which simulate ocean acidification, their fertilization success declined to about 52%, and the number of larval settlers declined by 73%. If these declining trends continue, then coral reefs are in a great amount of danger. So, should we be worried?
As I said before, there are already some predictions for how drastically the ocean's pH will change in the future. This graph shows us an estimate for the next 100 years, but you can see that there are a few different lines. This red line shows what will happen if we continue at our current level of carbon emissions. The pH of the oceans will decline very quickly and keep declining far into the future. But the different models shown here are based on different amounts of carbon emissions. If we reduce our emissions by a little bit, we get the blue lines in the middle, so the pH will still decrease, but not quite as quickly. If we work to drastically reduce our carbon emissions, we get the gray line, which shows the pH eventually leveling off, but it's important to notice that even on this line, the pH is still lower than where we're at right now, and it'll continue lowering for the next 50 years before it levels off. This is going to have huge impacts on marine life. Dr. Rebecca Albright is one of the experts on ocean acidification. She's a curator at Cal Academy of Sciences in San Francisco, and she studies the effects of ocean acidification on corals. When we asked her what impacts ocean acidification will have in the future, the major consequence that she talked about was that it impairs growth and reproduction. These are the two recovery processes that corals need after they undergo stress from things like a hurricane or a bleaching event. Acidification slows formation of the shell, so this means that corals can't recover when they need it most, and this applies to any calcifying creatures like shrimp, lobsters, or mussels. This could even impact the sand on our beaches because a large portion of sand is made up of broken shells. According to Dr. Albright, one of the biggest areas of concern for us on the west coast is oyster hatcheries because baby oysters can't form shells in acidic water. This leads to very sudden population declines and prevents new generations of oysters from growing and reproducing. In nature, oyster reefs provide physical structures for other animals, just like coral reefs do, And shellfish in general provide a lot of jobs for people. So ocean acidification not only impacts the environment, but it impacts our economy as well. Across all calcifying species, ocean acidification might lead to smaller, weaker shells and shorter lifespans because these animals can't repair or maintain their hard structures. As a result, some organisms may go extinct because, like with oysters, their babies won't be able to form shells and move into the adult stage, which prevents them from reproducing. This also impacts other fish and marine mammals in really drastic ways because a lot of calcifying organisms, like shellfish and plankton, are low on the food chain. Disruptions at the bottom of the food chain impact all the other species above it, and this includes humans because, like I said, a lot of people around the world use fish or shellfish as their primary source of protein.
So let's talk about solutions. Woo! Seagrass. Seagrass is extremely beneficial to coral reefs as they photoregulate and take in carbon dioxide. With this said, some scientists believe if there were to be an increase in seagrass, it could potentially reduce the high CO2 concentrations we see in oceans. Another thing we can do is reduce carbon emissions.
Reducing carbon emissions is going to be key in slowing down ocean acidification. We can each take steps to reduce our individual carbon emissions, but it's going to take a collective effort to make significant changes in the right direction. Easy things that we can do include walking or biking instead of driving, and reducing electricity use by turning off the lights whenever you leave a room, unplugging your electronics when you're not using them, and limiting how often you use air conditioning. But most importantly, it is important to research other ways to lower our carbon emissions because, unfortunately, a lot of factories and agricultural processes are responsible for the majority of global emissions. This means that even if we all make individual changes to our own habits, at this point, it might not be enough. Businesses and industrial processes must also change to help our oceans long term.
And thank you so much for joining us on this Summering of Learning. I hope you guys learned a bit more about ocean acidification and coral reefs. Thank you. Bye!